Now, this was the big tornadoes that occurred back 2 years ago. This was the tornado that was moving out of eastern Shelby County into western Rush County and eventually destroyed that covered bridge in the little town of Moscow. These are the storms that caused that damage that particular day. This is the one supercell that caused the damage over in Shelby and Rush counties. This particular one right here is the one that did a lot of damage at Camp Banterbury. Now these were actually, it almost looks like, I think they were on the ground at the same time. Now let's separate out these two pieces of information here so we can look at both the reflectivity data and also the velocity data. So you can see the well-defined hook-shaped echoes in both of these storms. And actually this is a little bit tricky here because you actually have two circulation centers embedded in this storm. One over in this storm over here. Over to the right-hand side, you see where you have this red splotch in this sea of green. And the same thing here, this tiny little red splotch matched up with this brighter shade of green there. And over here, this red splotch here matching up with actually those light blues. Remember, green is inbound, red is outbound. Our radar is located up to the top of this image here, so green inbound, flowing that way, red outbound in the opposite sense. So what you are seeing there, when you're seeing these red and greens right next to each other, that's an indication of a rotation center. That's that mesocyclone or low pressure center. And again, think back to the scale or the intensity. Darker reds and greens, weaker wind speeds, bright greens, bright reds, strong wind speeds. So in the case of these mesocyclones, the brighter the greens and reds, the stronger the rotation. And if a tornado occurs, probably a stronger tornado, and that's in fact exactly what took place in this scenario. The brightest of all three was the one on the far right-hand side. That was the one that destroyed the bridge in Moscow. That was an EF3 tornado with winds about 150 miles an hour. Over here next to Camp Banterbury, you can see it's not quite as strong looking. That one was an EF2 with winds about 125 miles an hour. And then this small one that you see right here is actually not even developed a tornado at this point in time. It's simply the startings of the development of the rotation in that part of the storm, and that's this hook segment that you see right here. Let me go ahead and put a circle on there to help identify here. And actually this one here, I think that circle is on a line here. This notching that you see right here is representative of where the rotation center is right here, which is what's taking place right there. So really, these circles I have over on the left-hand or right-hand side are a little bit off-center there. But so let me remove those. This one here, again, not real strong, was just beginning to develop, but by the time that this storm moved over here to the northeast of Greensburg, which is right there, right up there to the northeast of there, it produced a little EF1 tornado. So by utilizing your velocity data, and I haven't gone to the full description of these yet because you have two different types of velocity data you can look at. One is referred to as base velocity data, which is the one that you want to use when you're looking for straight line winds that may be coming from squall lines. When you're looking for evidence of rotation in storms, especially storms that have this hook echo on them, what you're going to do is in fact what you might want to do is lay up two radar images. One, the reflectivity on the left side, bring up another tab, the velocity data on the right-hand side. And when you're looking at hook-shaped echoes like you see here, what you want to do is use the storm relative velocity data. So again, velocity, you've got base velocity for straight line wind, and you've got the relative for rotation. So relative rotation, you want to use that for your storms that have rotation. It'll do a better job of identifying for you the strength of the rotation. The reason for that is that we're literally subtracting out the forward motion of the storm, so you're getting more of the pure rotation that is left behind in the information. So again, velocity data, really an important tool to use. Now, cloud features to watch for when they are well off in the distance, the anvil and the overshooting top. We'll talk about that in a moment. The more important ones are the ones that are close to the ground that produce the tornadoes. It's this rain-free cloud base from which an isolated lowering or wall cloud develops, and this rear flank downdraft and how it wraps into the storm and how it plays a role in tornado development. So let's take a look at these here. The mesocyclone, again, the result of changing wind speed and direction with height that sets up your rotation. It's wind shear is how the meteorologists refer to that. And the stronger the wind shear, the greater the potential for developing rotating thunderstorms. Regarding the anvil, that's the top of the storm. You can see it in each one of these examples here. And the more sharp and well-defined the edges are on these anvils, the stronger the updraft. And the stronger the updrafts, again, the larger the hail may be, and in all likelihood, what goes up really fast usually comes down really fast too. So you can have very strong downdrafts that occur with storms. So again, notice the look of these. The more sharp and well-defined those edges are, as opposed to fuzzy in appearance, the stronger the updraft. The same holds true, too, with regard to this feature known as the overshooting top. In this video in the center, you can see that overshooting top pop over just a couple of times there. In the still image, you can see it quite nicely here, how that cloud element is extended well above the normal leveling off point. And that's simply an indication, once again, of this updraft that's taking place. This air has so much momentum moving upward so quickly, it can't stop where it's supposed to. It goes above and beyond that. And again, it's simply an indication of a storm that has a very strong updraft, one that likely may be a severe weather producer. Now, normally when you're able to see these features, the storm is well off in the distance, unless you're watching it way out to the southwest, and in fact you're watching southwest and it's northeast bound, you probably just have a lot of cirrus and streaming at you, so you likely won't even be able to see that overshooting top. More than often, if you're seeing the overshooting top, it's at a distance way far away from you, and it's not likely to be coming to your location. So that's why I want to focus down to the bottom part of the storm. If this is coming to your area, you really want to be paying attention to this. The upward spiraling air that's taking place in the updraft region, underneath it, in the vicinity of what we call the mesocyclone center, the wall cloud, from which your tornado develops from. That's the key element that you want to be watching for. And you're watching for persistent and organized rotation, like you saw in this video clip here. That lowering of the cloud base that may eventually rotate and eventually produce a tornado. It initially starts out as a rain-free cloud base, which simply is a representation of where the updrafting of the air is taking place. And because the air is rising, generally in most cases, no precipitation is falling from that zone, and that allows you to see the cloud base quite distinctly, like you can see here and like you can see here. Now, the image on the lower left, notice the sky underneath it, a little bit fuzzy looking. There's actually a little bit of rain coming out of this rain-free updraft base, so it's not truly rain-free in that circumstance. Notice also the one on the lower right-hand side, how you have this segmented cloud below that yellow line. That is the development of the wall cloud, or an isolated lowering of the rain-free cloud base. And that represents the core of the strongest rising air currents that are developing within this storm here. Now, what's important over the course of the life cycle of that wall cloud is at some point, if it's going to become a tornado-producing storm, that wall cloud is going to need to show rotation. Now, in the vast majority of circumstances, the rotation actually develops up at the mid-levels of the storm and works their way down towards the base of the cloud, and eventually it works its way down to the ground. And through that process, it takes a matter of time before that wall cloud will start to show rotation. And so you might be capturing it early on in this life cycle and see no rotation. It might be a couple counties downstream before that rotation is present, or it may have started a couple counties west of you, and by the time it got here, there was no question that there was rotation in that cloud element. In this one here, here is your wall cloud, the isolated lowering of the rain-free cloud base. In this image here, on the left-hand side, there's your rain-free updraft base. To the right-hand side, that's your forward flank downdraft rain. And at times in between those two boundaries, updraft and downdraft, that's potential area for large hail to form. So you want to keep that in mind. If that area is coming your way, you might have some big hail come with it. A couple more examples of rain-free cloud bases and wall clouds. The upper left-hand side, the entire cloud element you see there is rain-free updraft base. This segment that's hanging down right here is the beginnings of the wall cloud. On the lower left-hand side in the black circle, your rain-free cloud base. This element here, a little bit below all the rest, that's your developing wall cloud. And in the upper right-hand case here, the entire cloud structure that you see is rain-free updraft base. This segment right here to the right of the tree is your lowered cloud base or your wall cloud, and actually right here is the tornado that's coming out of that particular wall cloud.